Hello, and welcome to the Logarithms and Exponent Applications Part 1 video. In this video, we're going to be going over 3 of the 5 equations we will need to know. The first one we won't use as much, so it's really more like 2 equations. Or if you think about this like the coformative, this is going to be parts 1 and 2 of the coformative. In the next video, we will continue with the rest of our equations and parts 3 and 4 of that coformative. So the equation that we're not going to use as often is this one right here. Y is equal to a times b to the x. The reason being is that we've used that for graphing and writing equations. However, in a story plot problem, there's normally a lot more features or variables that go into it. So for this equation right here, we're going to take a look at problem number 14. So I'm going to move this down to problem 14. Zoom in a bit, and then I can explain the equation. So the equation is y is equal to a times b to the x, where x is your time, b is your multiplier, a is your start amount, and y is your end amount. So let's take a look at problem 14. I'm going to highlight along the way. It says a bunny colony is doubling in size. So our multiplier is times 2. It says every 6 months. There are 2 bunnies now. So this is our start value. How many will there be in 10 years? So this is our time. So again, this is our, sorry, I'm still on the highlighter. This is our multiplier. 10 years was our time. We have bunnies, this is our start. The only thing that's a little out of place is this every 6 months. Well, every 6 months, that's 2 times per year. So if I'm thinking of setting up my equation, I'm going to say, okay, well, y is equal to my start amount of 2 times my multiplier of 2. And then for my exponent, I might say that this is really 2x because it's happening twice per however many years this is. So I'm going to go through and plug in what I can. So if we're going to find y, well, this is going to be 2 times 2 to the power of 2 times 10 for a 10 years. So starting with 2 rabbits, or 2 bunnies, excuse me, and they're doubling twice a year for 10 years. That's what this means. So if we want to simplify this, we can say this is 2 times 2 to the 20, or if we plug this in all at once, that is 2,097,152. So make sure that you write a sentence at the end of this, but for, we'll do that in class, but just for this video, for the sake of time, I'm just going to make sure that I give my answer with the correct units, which in this case, the units are bunnies. So that's what we'll be doing for those types of equations. Again, they will not happen very often. More often, you will find something that is compounding or something that is happening once per year. So let's go back to the top and take a look at that equation. So if we head back to the top, this is compounding yearly. You might also see the word annually, meaning once per year. But we're going to have a is equal to p times 1 plus or minus r to the t. So although the letters are different, a lot of the meanings are the same. So the a is the end amount, p is the start amount. It's called p because it's the principal amount, so it's the starting amount. T is your time, R is your rate, or the decimal of whatever percentage you have, and then this plus or minus right here, it's not always going to be plus or minus, it's either positive or negative. So if it's plus, means that there's increase or growth, and then there's minus if it's decreasing, depreciating, meaning losing value, something like that. So all of the things are still the same, just new, different letters. So let's take a look at problems 5 and 6 to see a little bit more about that. So if we take a look here, it says, let's see, where's my highlighter? There we go. Brian takes out a loan for $32,000. He's paying 6% annually compounded interest on the loan. Okay, so let's see what we know. I'm going to move this over. So he's paying that extra amount, so that tells me that that's moving up. I'm increasing by the rate of 6% for that interest, and I'm starting with that $32,000. So overall, to write my exponential equation, I can say that we have A is equal to 32,000, my start amount, a 1 plus 0.06, which is my rate, to the power of t. You can also add the 1 and the 0.06 and get A is equal to 32,000 times 1.06 t. I will accept either of these answers, however, I will be using this specific equation as we continue forward. So the next question says, how much will he owe after 10 years if he doesn't make any payments? So that is our time now. This is our time, so 10 years. So I'm going to try to find A of 10. So it'll be 32,000 times 1.06 to the power of 10. Now you can do this all at once. You can do it piece by piece. Just make sure that when you're using your order of operations, you would do 1.06 to the power of 10 first, because exponent comes before multiplying. Once you plug this into your calculator, you're going to get 57,307.12. This is actually super decimally, but since we're dealing with money, we're going to round to the second decimal place because pennies exist. So again, normally we would write a sentence, and we'll do that in class, but for the sake of time, I'm just going to make sure I'm using the proper units and sticking a $sign in front of my answer. So that's what happens if we're something is increasing. But what if, like in the next problem, it's decreasing or depreciating? So we're going to use 7, 8, 9, and 10. I know it feels like a lot of questions, but we'll go through it pretty quickly. So in this example, Chris bought a house for $340,000. It's depreciating at 10% per year. Okay, so he paid this much at the beginning, so it's our start. It's depreciating, so it means it's losing value at a rate of 10%. So if we want to write the equation for this problem, we're going to have A is equal to 340,000. So I'm just moving something in my notes. Times 1 minus 0.10 to the power of t. So again, we're losing, or it's depreciating 10% each year. So I will accept this, or you can combine, you can subtract the 0.1 from the 1 and get A is equal to 340,000 times 0.9 to the t. So this is the one that I'll be using in the next few problems, but just know that's what you can have. So for problem 8, how much will it be worth in 5 years? So since it's depreciating or losing value, we know that our answer should be smaller than 340,000. So we're going to find A of 5, which will be 340,000 times 0.9 to the power of 5, which is 200,766.60 cents. So again, this is less than our original amount because it's losing value. We would normally write a sentence, but for right now, I'm just going to make sure I'm using the proper units. And make sure to round to the second decimal place since we're dealing with money. Now the next question is a little bit interesting. So, I forgot to highlight. So this was our time. How much will it be worth in 5 years? But the next question is, what will it be worth 5 years, or what was it worth 3 years before she bought it? So this is going back in time. So if we're going back in time, we're going in the negative direction. So I'm going to find A of -3. So we're going backwards in that. And that's going to be 340,000 times 0.9 to the power of negative 3. Now, since it's depreciating, going forwards in time, backwards in time means it's going to be gaining or earning more money, or gaining value, I should say. Oh, I'm also missing a 0, in both of these problems. There we go. So our answer should be bigger than 340,000. So when we plug this into the calculator, we get 466,392.31. So it was valued more 3 years ago than it is now or in 5 years from now. So again, normally we'd write a sentence, but for right now, putting in my answers. So this is the logarithms and exponent application. So far we've only been dealing with exponents, but what about those logs? Well, for problem 10 it says, when is it worth $400,000? So now we have our end amount. So this is the end, but we need to know our time. We don't know our time. And since time is our exponent, if we have to solve for time as our exponent, well, we're going to have to use logarithms. So now when we set up our equation, I'm going to zoom in a lot because I did not leave myself a lot of space when making this. We're going to have 400,000, make sure you have enough zeros, is equal to 340,000 times 0.9 to the t. So this is like we're setting up our exponential form and we want to change it into log form. But before we can do that, we have to get rid of everything on the outside of whatever's with our exponent. So I'm going to divide by 340,000 on both sides. Now I'm going to keep this as exact as possible, and this turns into a super messy decimal. So if you take a look at what fraction this becomes, this reduces to 20 over 17. I am okay if you use the decimal instead, just make sure to keep the very long decimal in your calculator. We get to 20 over 17 is equal to 0.9 to the t. And now I'm like, hey, you know what I have? I have a base and an exponent and an answer. This is something that I can rearrange. So I'm going to move my work over here. So once we rearrange this, we have log base of 0.9 of 20 over 17 is equal to t. Now, since we have a base of 0.9, that's kind of weird, we're going to use our change in base formula. So we end up with log of 20 over 17, or whatever your decimal is, divided by log of 0.9 is equal to t. So I'm going to plug that whole thing in my calculator and get that, hey, when will the house be worth, or when was the house worth, $400,000? Well, since that's more than our starting amount, we end up with a negative number. We get t is equal to negative 1.5425. Since we're dealing with time, I'm going to round to the fourth decimal place here because we have days, minutes, seconds, that type of thing. So what does that mean in the context? Well, it means that the house was worth $400,000 1.5425 years ago. So that negative means we're going back in time. So remember, you subtract within the equation when you are depreciating or losing value, and then you plug a negative in for the exponent whenever you're going back in time. So that's what happens if something is compounding yearly. But what if it's compounding more often than that? Well, let's take a look at just two more problems. We went right past it. Part 2. Part 2 says that we're compounding, quote unquote, n times per year. So you may be compounding semi-annually, which is twice per year. You may be compounding quarterly, which is 4 times per year. Or you may be compounding monthly, which is 12 times per year. So everything in here is almost exactly the same. The only difference is that n. And that n is the number of times per year. So A is still your end amount, P is still your start or your principal amount, R is still your rate, T is still your time. Now we just have the addition of N, which is the number of times per year. So it's really, really similar to the compounding annually or yearly. Now there's just a specific number of times. So let's take a look at number 15 to see what that might be like. So let's see, it says you invested $1,250 at an interest rate of 6.5% compounded quarterly. Calculate how much interest you earned on your investment after 11 years. Okay, so taking a look at this problem, I can see that we have our starting amount of $1,250, an interest, I'm just going to circle it around a lot of space, rate of 6.5%, and it's compounded quarterly. So if it's compounded quarterly, the number of times per year is 4. So calculate how much interest you earned. So we want just the interest, not the total amount, of your investment after 11 years. Oops. Or at the time of T. So when I set up my equation, I'm going to have A is equal to my start amount times 1 plus the rate, or 0.065, so it's the decimal version of the percent, divided by 4 to the power of 4t. So this is my whole equation. It's not super pretty, but that's okay. When we try to find how much there is after 11 years, well, 1,250. If you find this in your calculator, it's actually a fairly nice number. So 0.065 divided by 4, I'm going to add that to 1. You get 1.01625 times 4 to the power of 11. So we're plugging 11 into our equation. Or 1,250 times 1.01625 to the power of 44. And once I plug this into my calculator, I'm going to get 2,540.59. Again, make sure to go to the second decimal place since pennies exist. So this is how much we have total, but we want to know how much interest we earn. So I'm going to take how much I have total, oops, and subtract how much we started with. And then I'll get my interest. So I thought I was recording, but this is the interest that we got, $1,290.59. So again, normally we would write a sentence, but we're saying this is our total interest that we earned in those 11 years. So again, what if we weren't using exponents? What if we were doing this with logs? Let's take a look at problem number 19. So for problem number 19, it says, here's my highlighter, you invest $250 at an interest rate of 1.5% compounded monthly. So we have our start amount, we have our rate of 1.5%, and it's compounded monthly. So number of times per year, it's going to be 12. So 18 is a little bit like what we just did. Whereas 19, how many years will it take to double your money? So question is, what is our time? And we want to double our money. So in this case, doubling our money is $500. So when will our end amount be $500? So it'll be 500 times 250 times 1 plus, let's see, our rate is be 0.015 over 2, pardon me, over 12, because it's 12 times per year, to the power of 12t. So I'm going to divide, first, I'm going to plug this into my calculator. Again, it ends up being a fairly nice number. So this will be 500 is equal to 250 times 1.00125 to the power of 12t. I'm going to divide both sides by 250 and get 2 is equal to 1.00125 to the power of 12t. Now from here, we have a base, we have an exponent, and we have an answer. So let's rearrange. We will end up with, actually I think I'm going to write this over here, just for some more space. We'll have log of, with a base of 1.00125 of 2 is equal to 12t. So that base is super weird. We're going to use our change in base formula to have log of 2 over log of 1.00125 is equal to 12t. And now here, to get t by itself, we can divide both sides by 12, but then we get like a weird triple fraction. So I'm going to multiply both sides by 1 over 12. That way on the right side, the 12s cancel out top and bottom. And when we multiply straight across, we end up with log of 2 over 12 times log of 1.00125 is equal to t, getting us our correct amount of time. So once I plug this into my calculator, I get that t is about 46.2387 years. And I'm rounding to the 4th decimal place because that was for time. So I know this was a long video. Feel free to rewatch as many times as you need to. But this is what we're working on today. Let me know if you have any questions, and I look forward to seeing you tomorrow.